Hello everyone, welcome back. I'm Dr. Yan-Fu Kuo, and today we will keep exploring embedded C on robotics. So the topic for today is HaViMo2, and we will learn how to use C program to control the HaViMo2 camera. This is a brief review of the camera. We know that HaViMo2 is a machine vision module that is designed for bioloid robots, and it works as a dynamic cell device. In a sense, it communicates with the CM510, the controller, through USART. Okay? So as a dynamic cell device, it must have an ID number. And this ID number is 100, and it is fixed. And here are some key specs of the camera. We will use them later. So first is the frame resolution. It is 160 by 120 pixels. Okay, and the frame rate is 19 FPS, frame per second. And it provides two image processing algorithms. First is the region growing. Second is the online grinding. And region growing is the one that we will use in our example. So what is region growing? It is an image processing algorithm used to segment the image into regions, or we also call it blobs, based on their color information. So color is the key. For example, if we have a picture like this, and it contains all sorts of different objects in different colors, and if we run a region growing algorithm, it will identify these objects and also give each of them an ID number. For example, this blue diamond, it will be identified and labeled, say, ID 1, and this green triangle, ID 2, and this brown diamond 3, and this yellow one 4, and this orange square 5, and this red one 6. And the algorithm will also tell us what pixels belong to which block. Okay, so for example, we know this blue diamond is composed of many pixels, okay, many of them, and we know every of them, okay. These pixels all belong to this block. And for a typical image, we know the coordinates is like this. We have X in this direction. We have Y in this direction. And the typical origin is over here down in the bottom left corner. So this is 1, 1. Okay? So for a pixel that is in the blob 1, okay, we say it's called Xi, and superscript 1. That 1 denotes that this pixel belongs to blob 1. Okay, we also know there's Yi1. Okay, so this is the coordinates of a pixel in blob 1. And we also know how many pixels belong to blob 1. So say that number is n superscript 1. Okay, this is the number of pixel. Okay, and how does this help us? So suppose this picture is taken by HaViMo2, okay, and you want to drive your robot toward this blue diamond. So what do we have to know? We have to know the center coordinates of this blue blob. So let's define it. The center coordinates of blob 1 is CX1, CY1, okay? And we need to find this. So how do we do that? Okay, we know each single, we know the xi, yi for each pixels in this plot. Okay, so we can do summation, right? Summation I, xi, 1, and we divide it by what? By n1. And we do this for our y, 2. And this is the center coordinates, okay? So what does HaViMo2 give us with its region growing algorithm? Say we have a sample image from HaViMo2 that is right here, okay? And remember, the origin of the image is in the bottom left and it's right here, okay? And frame resolution of HaViMo2 is 160, 120. It's up here, okay? So this is the x direction and this is the y direction, okay? So in this image, we have different, we have blobs in different color. So here, HaViMo2 identify this blue blob over here, okay? And what information does it give us? So see this line, okay? We check this is the second row over here, okay? And this is the data structure. Okay, let's see. For each blob, we have a ID number, that is the index here. And we know the color of it. Actually, this color can be defined by us through a lookup table. We'll talk about it later. And it also gives us the total number of pixels in this blob. That's the pixel. And the summation of x, summation of y. And it tells us the max x. So x increase in this direction, right? So max x will be over here, okay? And the minimum x, that will be over here. And max y, y increase in this direction, okay? So max y will be over here. The minimum y, that will be over here. In order to use the information from HaViMo2, we have to create a structure to store the data from camera. So here we have one structure, okay, to store the information for one color blob. Okay, so this is for one color blob only. So remember that for each color blob, we have an index, color, number of pixels, sum x, sum y, max x, mini x, max y, and mini y, okay? And these variables, they are different in their size, okay? So remember, here for index and color, and max x, mini x, max y, mini y, okay? Their size is 1 byte. For pixels, its size is 2 byte, okay? And for sum x and sum y, their size are 4 byte, okay? So in order to deal with that, okay, we have to use different type of variables, okay? So here we have unsigned integer 8. The 8 means is 8 bit, that is 1 byte. So 1 byte for these 6 different variables, okay? And we have 2 byte unsigned integer 16 for number of pixels, and 4 byte unsigned integer 32 for sum x and sum y, okay? And the name of this structure is HaViMo2 region T, okay? Now, we also need another structure to store the information of all the color blobs. And remember that HaViMo2 can provide the information of up to 15 color blobs, okay? So we need 15 of what? 15 of this data structure goes to here, okay? And the name of this data structure that store all the color blobs is HaViMo2 region buffer T. And we also need the computer to recognize the name of a color. So for human, we can remember the name of a color easily. We know black, teal, red, green, purple, white, cyan, magenta very well. But for PC, they only understand a number, okay? So we have to use the enumeration tool to give each color an ID number. So black, we give ID number 0, teal, that is 1, red, that is 2, and green, that is 3, purple is 4, white is 5, cyan is 6, and magenta is 7. Okay, so once we write purple in the C program, okay, computer can find, okay, that means number 4. Now let's see an example. Okay, and in this example, we're going to learn how to do pen tilt control with HaViMo2. And the example of the example is in this picture. Now, imagine that this is the head of a robot, and we have a HaViMo2 in the head, okay, and the camera represents the eye of the robot, okay, and what we want to do is we want the robot head to track an object in a specific color, and in a sense that the head is always front-facing that object. So what do we need? We need to control 2 motors, okay? And one motor is doing left and right, is turning the head left and right, and that's called the pen motor. And we need another motor that is moving the head up and down, like nodding your head, okay? And this is called the tilt motor, okay? And be careful about the setup, okay? So see that the shaft of the motor, of the pen motor is down, and the shaft of the tilt motor is in the left, okay? You have to set this up right, or the example code will not work for you, okay? And the specific task in this example is first to obtain color blob information from HaViMo2. And we talked about the data structure, but how to read that, I will show you, okay? And also to identify the center coordinates of the interested color blob. And this is just doing some calculation. And then the next one is to move these 2 motors, okay? In a sense that HaViMo2 is always front-facing the color blob. After you set up the hardware, you should have something like this. Okay, so here we have a pen motor, a tail motor, and HaViMo2. Okay, and all of them are connected together and also connected to a CM510 over here. Okay, and we have to set up the ID number of the motors and the lookup table of the HaViMo2 correctly so that CM510 will work with them. Okay, so the pen motor, it has a ID number 19, and the tilt motor ID number is 20, and we have a lookup table, a color lookup table that is stored in the HaViMo2. And this is important because the C program that we are going to write will be stored in the CM510, right? And CM510 has to control the pen motor and also control the tail motor, and it has to obtain color information from the HaViMo2. Okay, so each of the setup has to be correct. Okay, so how do we do that? How do we set up the motor ID number? We can use the Robotis tool. Okay, here we use the manager tool. Okay, and we connect to the CM510 controller. Here we will see that two X12 are connected. Okay, and how do we change the ID number? We can change that over here, right? Okay, and here you can also see a device with ID number 100 here. That is your HaViMo2. Okay, and now this is all set up correctly. And also, we have to set up the HaViMo2. And how do we do that? To set up the lookup table, we have to use the HaViMo GUI tool. Okay, and we can connect to the HaViMo2 through CM510. So here in the connection type, we select CM510, and the connection port is COM6 on my PC. And I click connect, and here in the button it says port open. Okay, that means we find the CM510. Then we go click check camera. Okay, it says the HaViMo2 found. Okay, so and next thing is that I want to track a board like this. It is in green color. Okay, so I want to take picture of this board. Use the HaViMo2 over here. Okay, so back to the HaViMo GUI tool. Okay, I click the sample image. Okay, the picture it takes will download to the screen now. And here, because the green color is color 3, so I choose color 3. And in the original image, I click this green board, and of the colors on this board will be select, and it will be the color 3 in my lookup table. Okay, this is almost all filled. Okay, so you can see that the color I select is in the lookup table overlap over here. Okay, now I want to store this lookup table in my HaViMo2. So I click flash LUT over here. Okay, and it start uploading. This will take a while. Okay, still working on that. Okay, then I disconnect my GUI program with the HaViMo2 by clicking the connect again. Okay, now close this tool. Okay, and now the setup is complete. Now I'm going to explain how the program in this example works. So first thing to do the pen tilt control is to read data from HaViMo2. And to do that, we have to define some variables to store the data. Okay, and we have a variable H2RB, that is HaViMo2 color block, that is used to store the information of all the color blocks from camera. Okay, and this is basically the structure that we defined previously, this one. And we have another variable, tracking color. Okay, and that is used to define what color we want to track. And another variable called track found. And this is to identify if any color in those color blocks match to the tracking color. Okay, and also another two variables to store the center coordinate of target. So for example, if this green ball is the one we want to track, okay, and we found it, and we have to calculate where the center of this green ball is. Okay, so the center will be calculated and stored in these two variables. Okay, will be target X, target Y. Okay, and here we create a routine to store the information, to process the information from HaViMo2. Okay, and the name is process image. It has one input, the tracking color over here. Okay, and it doesn't have any output, but it does store the process information into these variables. Okay, and let's see what it does. Okay, so first is it goes to retrieve the color blob information from HaViMo2. Okay, and store the information in the variable we define, H2RB. And then next, it go check if any color blob in H2RB matches to the tracking color. Okay, and if there's any match, then it calculates the center coordinates of that color block and store them in target X and target Y, and also enable the track found. That means make track found larger than 0. Let's see the example program. Now let's see the example in Eclipse. Okay, and the project is HaViMo2. Okay, and let's click on main.c and see the program. So in the very beginning, here we define the variables. Here we have H2RB and also the target X and target Y and track found. Okay, and the H2RB is the structure we define, and it is stored in dynamic show address tables.h over here. And we search it. Okay, it is right here. Okay, and remember we have another structure that is used to store information of one color block, and that is this one. Okay, and here we also define the routine, process image. The routine is in the very bottom of the program code, okay, right here. Okay, and in the beginning of the routine, first we assign an initial value 0 to track found, and we will use that later. Okay, so what does process image do? So first, in this section, it reads the color blob information from HaViMo2. Okay, so the first thing it does is to pin the camera. Okay, and if the camera does not respond, that means it is easy or it is not properly connected. Then we return to the main program. And if it does respond, okay, then we go retrieve data from HaViMo2. And that is this line. And after data is retrieved, we have to let camera keep capturing the image. And that is this line. Okay, so until now, we obtained the color blob information from HaViMo2. And we want to examine if color of any blob matches to the tracking color. Okay, and that is right here. Okay, remember that we have 15 color blobs. Okay, and we are going to check every of them. So first thing we do is to see the index of any color blob, RV, if it's equal to 0 or not. If it's not 0, that means that color blob is valid, okay? And then after find that color blob is valid, we want to check if the color of it matches to tracking color, okay? And that is right here, okay? And after we found, okay, there's a match, what do we do? Okay, we want to calculate the center coordinate of the color blob, and that is right here. So remember that what we do is we divide sum x by number of pixels. Also divide sum y by number of pixels, and store these two in target x and target y. Okay, and after that, we store number of pixels in track found. Okay, so why are we doing this? And in the example, we want to track a green colored blob, but in the image that captured by HaViMo2, there might be more than one colored blob that is green. So we really want to do is to track the largest color blob in its pixel size. Okay, so we store the number of pixels in track found, and we keep checking if any colored blobs they are green too. And if we find another one, we call it a new match. Okay, and we compare the size of the new match to the previous match. Okay, and if the size of the new match is larger, then we use the information of that color blob. And if not, we just keep the one that we had. After we obtain this color blob information, we'll control the pan and tilt motor based on this information. So how do we do that? Now this is the bird view of our setup. We have a camera, HaViMo2, that is on top of an X12. And this X12 is the pan motor. So in this example, I'm going to talk about the pan motor only. And it is similar for tilt motor. Okay, so suppose this pan motor has an initial position at 150. Okay, and we use one variable, head H position. That means head horizontal position to record the current position of the pan motor. Okay, and what's the value will be? Will be 512, right? So 150 is 512, and 0 is 0, and 300 is what? Is 1023. Okay, and for our camera, there will be either a CCD or a CMOS sensor that is here. Okay, and this is the center axis of the sensor. Okay, and the center position of the sensor in the horizontal direction will be what? Will be CX, right? And also for the camera, there will be a focal point. Suppose it is right here, okay? And the projection of the green ball, we are tracking will be here, and that location is target X that we obtain from HaViMo2, right? So what's the objective? We'll move the pen motor such that variable target X will be equal to Cx, right? Okay, so we define the difference between these two variables as arrow. We call it delta. So delta is target X minus Cx. Okay, and what is our control rule? Now we want to change the current position of the pen motor, and that is recorded in this head H position, right? So the new head H position will be the old head H position plus or minus the delta times again K. So K is a real number that you choose. It's the gain. And it has to a larger than 0. Okay? Now here, we have to choose it's a plus or minus. Okay? So how do we do that? Now remember, in our setup, okay, okay, the X increase in this direction. Okay, so target X is here, Cx is here, and we know target X is smaller than Cx, right? So that makes our delta smaller than 0. Okay, the delta is smaller than 0, right? And if the ball is on left hand side of the camera, we want to turn the pen motor counterclockwise, right? And in that sense, we want to increase or decrease the head H position, increase or decrease. Because this is 512, and rotate to here is 1023, right? So we want to increase the head H position, okay? And this is minus, right? And K is plus. So we have to choose minus over here, okay? So let's go check the program. And this is the program to do the pen tail control. And it is in a while loop so that we can keep tracking the object. Okay, and here we call the process image and give it the color green. Okay, and once that we find a color block that is green, and this track mount will be larger than 0, okay? And we will process this code, okay? And here is how the pen motor updated. So we have the head H position that is equal to head H position minus this target X minus 80 and divided by 2, okay? And we know the center of the HaViMo2 is 80 in the X direction. And here the gain is chosen to be 0.5. Okay, so this is just a typical choice. And we can do that on the tilt motor too. Okay, so it is doing that. Okay, and after we update the motor position, we have to check if it goes beyond the boundary. So for typical X12, it rotates between 0 and 300 degrees. And the position limit will be 0 and 1023. Okay, so once it goes beyond that boundary, it stays at the boundary. Okay, and it is the same for tilt motor. But because of our setup, we doesn't go down beyond 450. So 450 is the limit. And after we update the pen and tilt motor position, and we write that position into the pen or tilt motor. Okay, so this is basically it. Okay, and now let's see how it works. Now we want to download the program to CM510, and to do that, we have to use Robotis and the terminal program, the terminal tool, and connect to the CM510. Okay, and download the program. The program name is HaViMo2. Okay. Now, after you press the start button, the CM510 will initialize the position of the pen and tilt motors. Okay, and then you press the U button, and it will start to track the object that you want to track. Okay, so see that it keeps tracking the green board that I have. Okay, and you cannot move the object too fast. It doesn't do that. Okay, you have to move it slow and smoothly, and so the program is doing pretty good. Okay. So this is the example that I have for today, and for practice, I'd like you to set up the HaViMo2 on a smart card and use the smart card to track a tennis ball. Okay, suppose the tennis ball is say 1 meter away from smart card, and you have to drive that smart card toward the tennis ball and to within 10 centimeters in distance. Okay. And all you have to do is just to modify the program that I provide. Okay, and this is for today. Thank you very much.